Welcome here, and I'm excited to talk about the dry pond crediting today. So first, we'll just start off, who is Opti? Opti is the world's leader in adaptive stormwater control, and we'll talk a little bit more about that. But they're committed to clean water and resilient communities, and we're going to get into what that means as we go. Next is the map of where our Opti deployments are throughout the US. So as I say, a world's leader in CMAC. CMAC is still very new technology. So as you hear the concepts and applications today, think about where they may apply in your area, in your industries. We're going to talk about quantity and quality today and the benefits of combining those in a smart way. So I think, you guys may have some new ideas for us throughout the Mid-Atlantic even. And in 2022, Opti was acquired by a firm called IACs. IACs is out of Brussels in Europe, and they're a global leader in all things water. So you'll hear quite a theme today as we go through on water treatment. Okay, and this is the quick agenda. So I'm doing the introduction now. We'll get into regulatory approvals, which obviously is very important. MDE and the Chesapeake expert panel have given approved Opti's technology for wet ponds and dry ponds. We're going to focus on dry ponds today, of course. And then Dr. G will tell you about how the design criteria and how to actually credit. And then Victor will take you through a couple case studies. All right, so this is our best slide for showing what CMAC is. So CMAC you'll hear referred to quite a bit. It's continuous monitoring and adaptive control. So continuous monitoring, we're going to be using things like forecast or sensor data, maybe even flood data downstream to make decisions about opening valves, operating pumps, moving water in a smart way. This could be moving water out of the way as the storm's coming in, or trapping and holding water for retention, reuse, or cleaning purposes, which is also kind of the big concept for how we're getting these TMDL credits. Opti can use not only the precipitation forecast, but we can also use web-based O&M portals and SCADA to make better decisions and to provide a real robust product to folks on a number of fronts. This, since we are talking dry ponds, you can imagine this is a hydrograph, of course. We've got time, and where the water is essentially in the pond. But picture a dry pond, it may be a grassy bottom, it may be mud, depending. But we're going to assume that it's dry. It is holding no water right now. And as it rains, this pond is filling up. And I like to say, a typical dry pond has an open orifice. So as dirty water or chocolate milk comes into the pond, it's essentially going right back out again. Opti has the ability to close that valve and hold on to that dirty water, and over time simply let the pollutants settle out, and then we'll open it to release the clean water. So the middle of this hydrograph is essentially where that storm is filling the pond up. As best we can drain that pond down if there was water in it before the storm to create the most volume that we can, and then catch every bit of the rain that comes our way. The kind of fourth column there is essentially where we're holding onto the water, allowing it additional residence time to clean. That's the derivation of these credits that you'll hear about today. And then basically we can hang on to it indefinitely if we want. But before the next storm, or maybe in just 48 hours or 72 hours, we're going to open the valve and allow that water out. And what's kind of neat is Opti can control the flow rate out. So if we're dealing with, outfall scour or stream erosion downstream, we can help mitigate that by simply slowing the flow on the way out of this pond. And these, while we monitor the pond's quantity and quality, we're bringing all these kind of stacked benefits. So today, you've already heard, if I catch all of the water during a storm event and hold on to it, it's not going downstream during the rain, which means I'm going to help alleviate any downstream flooding. In a wet pond, I can draw it down and create room before the rain, and that may alleviate backwatering effects. So I'm also alleviating flooding upstream, perhaps. And while I hold on to the water longer, that's where the cleaning comes from. That's where the water quality components come from. Hydromodification is the fancy word for slowing that flow out of the facility, and providing some integrity benefits towards the outfall in streams, receiving waters. And then last, all of this is in real-time data, so Opti provides a dashboard to the user, and they can literally see the benefits and how things are working. And if someone is in public sector and they're responsible for using stormwater fees and tax-paying dollars, they're able to kind of show the public how we're using this. It's like we're using these public funds to do exactly this, and we're measuring water quality benefits. If we're alleviating flooding, the public can even see that, but we also have real-time data that proves it as well. I think that's all. Those are the biggest benefits for Maryland, I think, that you'll hear throughout the theme today. Passing it over to Dr. Kathy.
Hi, I'm here. My Zoom froze up. I apologize about the delay, but so I'm here to talk to you about the regulatory approvals that Opti has acquired. We have received regulatory approval through both the state of Maryland and the Chesapeake Bay program. In January of 2016, the Maryland Department of the Environment, or MDE, approved the use of our CMAC system as a wet pond retrofit application to meet the MPDES MS4 Phase 1 permit requirements. And the pollutant removal efficiencies are going to be equal to those for structural treatment practices. In September of 2022, the MDE approved the use of Opti CMAC system as a retrofit for dry and dry extended ponds. Practices retrofitted with our CMAC system are eligible for 75% of the pollutant removal efficiencies for structural treatment practices. And to date, Opti is the only CMAC system that has been approved for this use. In November of 2016, the Chesapeake Bay program approved the use of CMAC for the enhancement of existing BMPs and for the conversion of existing BMPs. An example of an enhancement would be upgrading an older wet pond with CMAC, while conversion would be using CMAC to convert a dry pond to a wet pond, since the wet pond provides higher water quality credit. So I'd like to provide a little bit of background on how these regulatory approvals were achieved. To receive approval through MDE, an applicant must provide detailed information about the proposed practice. This includes a description of the practice and its proposed use, a description of the technology being used, and the results of field monitoring that demonstrates compliance with performance criteria. As part of our dry pond approval application, Opti conducted 18 months of hydrologic and water quality monitoring to demonstrate the benefits associated with CMAC retrofits. Some of these data are shown here in this graph. Within the Chesapeake Bay program, the approval of pollutant loading reductions and adjustments used in the Chesapeake Bay model falls under the purview of the Water Quality Goal Implementation Team. A BMP expert panel is formed and charged with developing definitions and pollutant loading estimates for proposed technologies and practices. The panel includes individuals with specific expertise and experience in water quality issues, and their recommendations must undergo a 3-stage independent peer review process, which also includes a public comment period. Applicants are required to submit information on how the proposed practice reduces nitrogen, phosphorus, and sediment, as well as references to available science and/or data documenting the practice's pollutant removal efficiencies. Now I'm going to hand it back to Victor to talk about design criteria and crediting.
Thank you, Kathy. So the first goal of any project is to deliver something with great outcomes, but also a project that is safe, secure, and reliable. And we do that through partnerships with you all, the local experts, whether it's A&E consulting firms and contractors, or it's customers with in-house engineering staff. So as a technology provider where we focus, we use over our decade of experience to support all phases of your project lifecycle, from planning all the way to O&M. And it's our goal to, at the end of the day, deliver to our core purpose of clean water and resilient communities. So what is the life cycle of a continuous monitoring and adaptive control project? Well, a lot of it is very similar to what you are all used to. There are some differences, which I'll point out, but our basic steps is through planning, the feasibility assessment, design and permitting, of course, construction, and then operations and maintenance. Now, we've done a webinar over the past couple of months, 101 on feasibility assessments and solution design. So I just want to point you to that hyperlink that you're welcome to take a look at, where we dive deeper into the configuration and layout of the hardware and specific modeling and simulation capabilities that we've developed over the years. Today, however, we're really looking at design and regulatory crediting from that regulatory lens, if you will. So we're focused on the feasibility assessment and what the objective and requirements are, the approach, and then the benefit analysis. The benefit analysis in this case is really looking at the water quality and the incremental credits that we can generate with the dry pond approval. And as many of you know, in Maryland, the dry ponds have historically not received any water quality benefit. And so we have an opportunity now to take an asset that has been primarily designed for flood control and generate water quality improvements and unlock a whole new tool in your tool set. So back to Kathy.
Got to unmute first. So evaluating the feasibility of retrofitting an existing site with an Opti CMAC system involves a three-step process, which is shown here. It includes a detailed site evaluation, confirmation that the site conforms to all regulatory requirements, and the calculation of water quality credits and benefits. So a site evaluation involves a thorough assessment of existing site conditions, and that includes the drainage area, the storage capacity, and the controllable volume of the existing BMP. The site must have adequate cellular connectivity and adequate power availability, either as line power or as solar. And finally, the stormwater management objectives associated with the site should be considered as well, and that includes existing water quality credit or upstream treatment. Review and approval by the appropriate authority is required when you're retrofitting a wet or a dry pond with a CMAC system. Numerous studies, surveys, calculations, tests, and data are required as part of that permit application to ensure that the addition of that CMAC system doesn't jeopardize the originally designed function of the practice or the structural integrity of its components. Some of the elements associated with the dam and the emergency spillway that must be addressed are shown here, but this isn't an exhaustive list, so designers should always refer to MDE documents for the complete list of requirements. In addition to verifying the hydrologic, the hydraulic, and the structural integrity of the practice, other aspects of the CMAC system must be considered. The dam of a pond must be classified as low hazard. The embankment must be less than 15 feet, and the total storage volume less than 20 acre-feet to be eligible for a CMAC retrofit in the state of Maryland. The system must be designed to minimize the resuspension of sediment at the outlet, and cold water protection strategies must be implemented in water use classes 3 or 4 watersheds. Outlets should be evaluated to determine the appropriate fail-safe position of the actuated valve, whether that's open or closed, and outflow rates must align with management objectives and pertinent regulations. Now, it's important to note that specific requirements may vary between wet pond and dry pond applications, so be sure to refer to the state's guidance documents. Finally, a detailed operation and maintenance plan must be provided as well that includes standard operating procedures that ensure proper function of the valves and the electronics associated with the system. In Maryland, the water quality credit is equivalent to the impervious acre credit, and that is determined from 3 BMP variables: the drainage area, the impervious acres within that drainage area, and the rainfall depth that is treated. Impervious acres within the drainage area are considered to be 100% treated for water quality purposes, when the runoff from the 1-inch rainfall event over the drainage area is captured and treated. So the first equation shown here is equation 1 from MDE's Accounting for Stormwater Waste Load Allocations and Impervious Acres Treated document. And it is used to calculate the impervious acre credit for structural BMPs when the rainfall depth treated is equal to 1 inch. When you're treating more than 1 inch of rainfall depth, additional impervious acre credits may be available. So using equation 9 from NDE's document, you can calculate the water quality credit for a total treated rainfall depth above 1 inch, although credits are only available for a rainfall depth up to 3 inches. Since dry ponds currently do not receive any water quality credit in Maryland, these equations would only pertain to a dry pond that has been retrofitted with an OPTI CMAC system. As part of the Chesapeake Bay TMDL program, pollutant load reductions must also be calculated and reported. Pollutant load reductions for upland BMPs are based on the pollutant removal efficiencies that are recommended by the Chesapeake Bay program. The equation used to calculate total nitrogen, total phosphorus, and total suspended sediment load reductions is shown here. The annual load reduction provided by a BMP is the product of the urban unit load, impervious acres within the drainage area, BMP efficiency, and the Phase 6 Chesapeake Bay model segment delivery factor. We'll talk about each of these variables in the next few slides. The urban unit loads are presented in Table 4 of the MDE document. These represent statewide cast no action scenario urban unit loads, and users must decide which load source best represents a BMP's drainage area. As we said before, pollutant load reductions for upland BMPs are based on the pollutant removal efficiencies recommended by the Bay program. Table 3 in the MDE document provides the removal efficiencies for BMPs associated with commonly used rainfall depths. But to determine the BMP efficiency for rainfall depth not shown in this table, you can use the adjuster curves that are provided in Appendix A. The example shown here is for a rainfall depth of 1 inch, which would be roughly equivalent to a 70% removal efficiency. The rainfall depth treated by a pond retrofitted with the CMAC system is a function of the adaptive control volume. As shown in the figure here, that adaptive control volume is the volume contained between the low flow invert elevation and the overflow elevation. This volume is the water quality treatment volume. And when you divide it by the impervious acres in the drainage area, it yields the treated rainfall depth. Wet ponds equipped with CMAC may use the full BMP efficiency rate associated with upland BMPs for a given treated rainfall depth, but dry ponds with CMAC systems may use 75% of that efficiency rate. This figure shows how the adjuster curve can be used to determine the total suspended solids removal efficiency for a retrofitted dry pond. By incorporating an OPTI CMAC system, the rainfall depth treated increased from 1/2 inch to 2 inches. Because dry ponds are not awarded water quality credit, the original credit would have been 0. But with the addition of an OPTI CMAC system, the BMP would be awarded a total suspended solids BMP efficiency factor of around 58%, which is 75% of the full credit associated with the 2-inch rainfall depth, which would have been around 78%. And finally, the Phase 6 model segment delivery factors translate edge of stream load reductions to edge of tide load reductions, and they are used in determining pollutant load reductions for the Chesapeake Bay TMDL. A table of those delivery factors is provided in Appendix L of the MDE document, or you can use the EOT factor map, which is provided on MDE's website, and a screenshot of that site is shown here. Now I'm going to throw it back to Victor to walk us through some case studies.
Thank you, Kathy. Excellent overview and all the tools and resources available to generate additional value from those existing stormwater BMPs. So the first case study we wanted to talk about was in Montgomery County, and the dry pond here is actually a very special one because it was the BMP that was used for the dry pond approval study, in addition to other data that we've collected from a number of sites across the country. So just a little bit of background. This is a little bit of a smaller asset collecting drainage from a residential area. So here are some of the statistics and the location. Drainage area about 14 acres and 5 acres of impervious. The existing facility was classified as a dry pond. And then through our existing conditions survey and feasibility, as Kathy mentioned earlier, we're able to determine and develop a control volume of 26,000 cubic feet. Again, that controllable volume is typically between our orifice that we're controlling with a valve or a pump and our overflow weirs that are typically the 2-year or the channel protection weirs. So it's using that water quality volume more intelligently. Here is a great photo of the site and all the components that are shown here during the monitoring study. So this was in April of 2017. Just to talk about the site, the inflow goes over some of the riprap at the beginning, and then the outlet structure is at the back of the photo. And the components, just as a reminder for CMAC hardware, we always have 3 components. One is a control mechanism. It's an actuated valve or a pump, a level sensor to determine the active level and storage volume available, and then the control panel that can be line powered or solar powered. And that control panel collects the data from the site and also communicates through cellular to our cloud-based system. And the calculations are all happening in the cloud in terms of when to open the valve and when to release the water from a both water quality and water quantity standpoint. So this site's a little bit more unique because it incorporated other elements of the actual monitoring study. At the right side there, we have the inflow auto sampler. And I just wanted to mention this study was done by a third party, MWCOG, that actually did the sampling and then brought that to the lab for analysis. So we had the inflow auto sampler and then on the outflow. So really trying to do a event-based comparison of inflow load minus the outflow concentration to determine the actual removal efficiencies. So what we looked at over the 20 storms is the upper and lower confidence intervals, but here's just a demonstration of what the mean removals were. So in some cases, like TSS, we exceeded even what the Bay retrofit curves suggest. On TN, we were about 75%. And then with total phosphorus, we saw some variability, but saw removals up to 38%. So again, this study plus some of our other sites across the country were really used to determine that 75% reduction factor from the Chesapeake Bay adjuster curves. So the credit calculations, this is using the same formulas that Kathy described earlier. So here are the actual metrics that went into what this site generated. So the adaptive control volume I mentioned earlier was that 26,000 cubic feet over the impervious area, which gave us a PE of 1.25. And so as Kathy mentioned, we have the 2 equations on the right with the water quality credits for up to 1 inch and then over 1 inch. So the water quality credit was a combination of both of those, since we were exceeding the 1 inch water quality standard. And this site generated 6.16 times the 75% reduction factor, so 4.62 acres. This is on the smaller end of some of our retrofits, but was strategically picked for the demonstration and the pollutant load reduction calculations. So the last case study we just wanted to highlight is a really exciting public-private partnership with Maryland DOT and Walmart and TNC and Prudential and MES, and KCI was the design engineer, but lots of folks went into this, but it was looking at using private land and commercial property to enhance water quality as a way to meet MDOT's MS4 compliance. So MDOT's Maryland Department of Transportation's big challenge was meeting their water quality MS4 permit compliance. They're a large phase one, and so their first 5-year cycle was about 4,600 acres of impervious surfaces they needed to treat. And so they looked at all the tools in the toolbox, so to speak, from stream restoration to BMP retrofits, outfall stabilization. But the reality with the DOTs, although they have a large footprint, they have limited right of way to do a lot of these improvements. So they had to really think outside of the box on how to generate those compliance metrics. And that's where this public-private partnership really came in. It was through the recognition that typically 70 to 90% of land is privately owned. And that's where a lot of our stormwater assets are currently built. And so if we're going to do watershed-wide restoration or statewide restoration, it creates a tremendous opportunity to tap into those existing assets for greater community benefit. So as I mentioned here, this was a partnership with Walmart stores. We did 3 pond retrofits with Opti's continuous monitoring and adaptive control. 2 out of the 3 were actually dry ponds. And so this also pushed forward this partnership and this dry pond approval as well. The 2 out of all 3 sites have been permitted and certified by MES. And as I said, 2 of them have been dry ponds. The other thing I want to mention is just not only the right-of-way challenge, but just the economics of building more infrastructure. Through this partnership, we were actually able to unlock some tremendous savings, and that quote at the top right kind of demonstrates the traditional approach of increasing storage with a pond and going from dry to wet. With our technology, we were able to successfully generate these credits at $40,000 an acre versus the $150 that they're traditionally used to with those limited right-of-ways. So not only was it challenging to generate those credits, but the economics make that bar so much higher. And on the bottom right, we're not going into the full calculations here, but on the bottom right is the actual certification from MES on the facilities, what the rainfall treated over the impervious was, and then the final impervious acre credit. In summary, Opti's promise and value proposition is really 3 major items. One is the economic savings, as you just saw on the last slide, 60 to 90% on savings and accelerated outcomes. That's achieved by optimizing both existing assets or right sizing or maximizing the footprint and control volume on new infrastructure. On the resilience front, it's in the name of the solution, continuous monitoring, adaptive control. And we call it adaptive for a number of reasons. One obvious one, hopefully, is that we integrate with the weather forecast. So we're using predictive technology to drive smart decisions on how these facilities behave to meet multiple objectives. The other element of adaptive that's really critical is the ability to change settings and configurations over time. The one thing we are certain about in the future is that change will occur, and our ability to update or reconfigure our system's performance allows us to adapt to future climate, future watershed development, and future regulatory compliance. And lastly, what comes along for the ride through continuous monitoring is improved safety and compliance and peace of mind. So this data is now feeding into annual compliance reports and providing information on targeted maintenance and getting ahead of bigger issues that could occur. And so I think we're just wrapping it up. We're ahead of schedule today. But Jennifer, if you want to bring this home.
Absolutely terrific. Thank you so much. We're going to open it up to questions. We do have Sean has a question for us in the Q&A box. He asks, retrofitting dry ponds using CMAC and use 3 and 4 thermally sensitive watersheds, right, could open up many opportunities for jurisdictions to gain impervious acre credits and TMDL load reductions, right? historically retrofit opportunities to dry ponds were limited in those watersheds to primarily submerged gravel wetlands. Right? So if we use CMAC instead of the traditional retrofit methods, right, can we provide a more economical solution for these water quality credits? Have we done this before, and how receptive have we seen MDE and DNR be with that approach?
Yeah, I don't believe we've actually done a retrofit in those use waters, Jennifer, but there has been interest around that. The dry pond approval letter doesn't exclude those areas. It specifically mentions that special considerations need to take place. We are working with Montgomery County, as I mentioned, and there is a desire to better understand how to use downstream temperature sensors and use this logic to actually help with thermal pollution and thermal impacts. You know, a simple example of that would be discharging at a much lower rate, which we already do, so minimizing the amount of thermal load, as well as discharging perhaps during the evening periods or when the temperatures downstream are lower. So we'd be very interested in working with someone on that and exploring that solution further.
Absolutely. Great. Lots of good questions coming in. One is going back to the regulatory, right, which I think is where a lot of our questions are going to be. But on the regulatory approval side, what does that permitting process look like to get these credits? Is it just show your math and we're done, or what does that look like from a permitting process?
Sure. So I guess the biggest thing I'll say is it does depend on your local conditions. And as Kathy mentioned, always referring back to MDE requirements is the best practice. But what we've seen specifically across many installations in Maryland is that with a retrofit, typically the disturbance of the outlet structure is minimal. Again, the outlet structure has to be in good structural integrity to add a valve and some of the control devices that we're discussing. So if we can minimize, typically we are disturbing less than 10,000 square feet of earth. So that avoids grading permits, for example, which can be a lengthy process. So mostly what we're doing is working with the local soil conservation district and going through the MD 378 checklist to determine that all those site requirements that Kathy mentioned are being met. So those include items like freeboard during the 100-year clogged condition for a wet pond, for example, the emergency spillway requirements, and some of the clay core requirements. So typically it's going through the process to determine that the site itself, even pre-retrofit, meets all the MD 378 small pond requirements. And then when we add Opti to it, we're looking at what is the H&H and water quality benefit. So that's why site selection, Jennifer, is such an important point here, is we want to find opportunities where hopefully we don't have to go through an extensive regulatory and permitting process.
Sure. Great. How many sites or how long has CMAC been present in Maryland? So, you said the approval came through 2016, but Opti's been around longer than that. Can you share a little bit more of the history in the region?
Yes, yeah. Our first installations go back to the 2015, 2016 when National Fish and Wildlife actually funded a dry pond bioretention and a wet pond retrofit, and that's where some of the early approvals came in. We've worked with a number of phase 2 communities, as well as currently we're working with 4 phase 1 Maryland permittees. So continuing, it keeps growing over the years, but we've been able to learn a lot and bring in better guidance for our A&E partners in particular. You know, one thing we're heavily focused on is how to improve design with O&M in mind. How do we improve operator access, safety, and minimize some of the downtime and maintenance costs? So over the last decade, it's been a great journey, and our product continues to evolve.
Right, terrific. What, see, next question here is what tools are available for our partners to use when designing CMAC? And where can we get access to said tools?
Great.
So I can touch on that real
please.
quick, right? It's
Yes.
go to our website. Please do. Our website, optrtc.com. There is a resources page there with design manuals, calculators, example projects, drawings, and review our past webinars. As we said at the beginning, we have 2 other webinars that are specifically going into this design process with feasibility studies, with focusing on the importance of that site selection, and then going into more detail on the solution design. What other resources, or how can we get in touch with people, Victor, that can help AECs learn more about CMAC?
No, I think that was a great suggestion, Jennifer. If you're not seeing something on the website, it's really easy to reach out to the team here, Jason, for example. But this is continuously being updated. We're trying to make our tools simpler to use and execute on. For those of you that haven't seen one of the recent webinars, we're really excited to announce that we have the ability to now simulate the full behavior on an event basis through SWIM. That's something we're excited to bring to our partners because that H&H piece, Jennifer, is so important. So those are pieces that you can reach out, and you have questions on any of this, we can help facilitate the process. I think we will share, or feel free to request it, a calculator for the dry and wet pond approval. So we've tried to create, simple spreadsheet tools that help unlock the benefits very quickly and clearly to our partners and customers.
Excellent. Do any of our attendees have something they want to share? If they want to raise their hand, or take yourself off mute, we'd love to hear from the crowd. In the meantime, I want to dive a little bit more into the H&H piece. So we've got all of our engineers on the line, and I'm curious if we have any modelers that are on the line, but what level of effort is required in the modeling here? And does Opti do the modeling for these types of projects, or is that something that we work with the consultants and our customers and partners with?
Yeah, we take a partnership first approach, so always supporting our partners and providing them with the guidance to help them through that process. And as you said, there's some design guidance on our website. Typically, for the modeling in Maryland, for example, to your question here specifically, folks are using TR20 or TR55 to look at just those 100-year or 10, 25, 100-year flood elevations with a fail-safe position. So those are I think the bare minimum to meet compliance. But beyond that, Jennifer, there's been a lot of talk about how do we balance multiple objectives. And it's really about using that storage more efficiently, both during large extreme events, but also during that water quality volume. And that's where the full simulation capability can really help us better understand how to meet both local goals and objectives, but also at the watershed level. One thing we didn't really get into today is what does this look like at a smart watershed, and how can we use this technology to now unlock improved outcomes beyond jurisdictional boundaries. And that's something we're really, really excited about in terms of the future and where we're headed with this. And simulation, as you can imagine, beyond the site level is a really important and critical component for us to understand routing and all those important KPIs.
For sure. Right.
And I'll just add, I think one of the themes that I didn't harp on at the beginning is like, we're talking this whole time about obtaining impervious acre credits from dry ponds, but that isn't always the main driver. Maybe we're trying to decrease flooding in an area, or look at ponds upstream that could help us do that watershed approach that Victor just mentioned. I think in that case, now our primary driver is resiliency first, and we're going to get credits on top of that. So if I'm an MS4 and I want to spend my dollars in the most effective way, I want to address resiliency issues and get these secondary benefits that really do count. I mean, you know, like Victor said, that example was only 4 impervious acre credits, but that's towards the smaller end of what these ponds can really kind of put out, if I may. You know, it's like that's pretty neat on the stacked benefits, and I know folks still have quite a ways to go in some parts of Maryland. So consider that if you're a resiliency planner or an engineer helping with that kind of concept.
Good point.
I'm going to share this last slide one more time to make sure that everyone has our email addresses. I encourage you to reach out to Kathy or Jason. Their email addresses are there to follow up with any additional questions or any projects that you might have that you would like to discuss further. You can, like I said earlier, go to our website at optrtc.com and access plenty of resources there. We'll follow up with a copy of this webinar, the video, and the slides to each of you in the coming days. So thank you all very much for your time, and we look forward to hearing from you all soon.
Thanks, everyone.
So long, gang.
So long.